Hyperbolas, 10-8. So this is the last of the conic sections before we start getting to like the applications and the word problems. Again, we're looking at the equations of hyperbolas a little bit differently than we did at the beginning of this chapter. But first, let's talk about real-life applications of hyperbolas. This is one of my favorite things, actually, in pre-calculus. I'm bummed that I can't be there in person to talk about this with you guys, but just some fun things to note here. Hyperbolas, where are they found in real life? So one of the really big things we're going to see in the word problems next week is equations of hyperbolas that represent nuclear reactors. So nuclear reactors are often built in the shape of a hyperboloid. It's a three-dimensional hyperbola. The reason we use hyperboloids as the shapes for nuclear reactors a lot of times is because it's really structurally sound. When it's built like this, it can be built with straight steel beams, and they can withstand a lot of things, especially like high winds and things like that. We really need our nuclear reactors to be super solid. So a hyperboloid is a really structurally sound shape. It also is really economical. It requires less material than any other shape, given its size. So something rectangular would require slightly more materials, be a little bit more expensive to build. So it is also economical, but structurally sound is probably the most important thing given a hyperbola there. All right, where else can we see hyperbolas? The speed of sound. So if you've ever heard of a sonic boom occurs when a plane starts to move faster than the speed of sound. So there's this like boom, and then what happens is the plane creates a cone-like wave, which you guys can see in the picture in the bottom left. And when that cone or that cone-like wave intersects the ground, what happens is it intersects in the shape of a hyperbola. So if you see the picture on the bottom right, that right there is our hyperbola, our shape of a hyperbola. It's when the cone intersects the ground. And we kind of introed this at the beginning of the chapter a couple weeks ago when I gave you guys inverted cones and we were passing planes through them. So the ground is essentially the plane that passes through that cone. And what happens is this: if you're standing outside of that curve, you can't hear the sonic boom. So you can only hear the sonic boom if you're standing on the ground at a place where that curve intersects or that wave intersects the ground. So only on the curve can you actually hear the sonic boom. Everywhere else you can't. And then the last thing there is on the left, the picture on the left, you can only see the sonic boom because there's humidity in the air at the time, but it's kind of cool. A couple of other things: gear transmissions are often shaped like hyperboloids, and then they create gear transmissions between two skew axes is what we call them. So that's another example. And then also, if you guys look at a lampshade in your house, you'll see that the lampshade casts a hyperbolic shadow on the wall if it's against the wall. And then if you've ever seen Dulles Airport, the roof has a shape of something really interesting. It's a hyperbolic paraboloid. So it's a three-dimensional curve, and if you intersect in one way, it's a hyperbola, and then in another way, it creates a parabola. So those are just different examples of real-world applications for hyperbolas. Let's talk about the geometric definition of a hyperbola. So we define it as the locus of points. So just like an ellipse, where we start with the locus of points, it's the set of points, but this time it's the difference whose distances d1 minus d2 form, that should be form, not from, from two fixed points, form the points on our hyperbola. So we call those two fixed points the foci, the focal points. Same as an ellipse, we've got focal points there, but in an ellipse, remember, we defined the definition as the sum of the distances from those focal points to a point on the curve. This time for a hyperbola, we're taking the difference of those distances. We're going to call that constant 2a again, and that's going to help us find other important pieces of information. But if we take a look at this animation here, we've got those two focal points labeled. Now we're taking d1 minus d2. We're calculating those values as we go along, and then we're plotting that point at that value. All right, important things to remember about a hyperbola. So different pieces of information fit differently between hyperbolas, parabolas, and ellipses. A is the distance from the center to either vertex. It's actually the same in an ellipse, center to vertex. And C is the distance from the center to a focal point. So also the same in an ellipse. However, we're going to see something different. A is going to be shorter than C in a hyperbola. The focal points now in a hyperbola are going to be outside of the vertices. So that was switched in an ellipse. Just something to note there. That means that the Pythagorean relationship is then going to change between A and C and B. So here's how we define everything for a hyperbola. Pause this if you need. I'm going to read through it. C is the distance from the center to either focal point. A is three things. It's the distance from the center to the vertex. The denominator of the positive fraction is really important there. And half the length of the transverse axis. So remember, the transverse axis was 2A. A is half the length of the transverse axis. And then the denominator of the negative fraction is B. B is also half the length of the conjugate axis. Now the Pythagorean relationship for hyperbolas changes then. That's what is different between hyperbolas and parabolas, or ellipses. We go back to the traditional Pythagorean relationship. A squared plus B squared is equal to C squared. C, the distance from the center to either focal point, is the longest distance for a hyperbola, which means that is essentially what would be the hypotenuse of our triangle. For a hyperbola, the eccentricity is greater than 1. Remember, the eccentricity measures how flat our curve is, and we calculate that the same way we calculate an ellipse, C over A. This time C will always be larger than A, so our eccentricity will always be greater than 1. Again, as mentioned in the last video, when the eccentricity is equal to 1, we have a parabola. All right, so very much like the last example, or the last lecture video, I would recommend skipping around, maybe not watching this whole video, but finding examples that you think you need to do in the notes and then go and do the homework. I will do all of the example problems in this video, but again, just skip around, see which ones you think you need to see or to watch, and then get started on your homework. Okay, homework. You are not going to follow the book instructions as usual. You're going to sketch a graph of the hyperbola, then we're going to label the vertices, foci, transverse axis, and conjugate axis, and then we're going to calculate the eccentricity and write the equation of the hyperbola. So you're going to do that for all of your homework problems as well. Okay, let's start with what we've got. The center of our hyperbola is 0, 0. We are told that we've got a focal point at 5, 0. Just going to sketch it. And we have a vertex at 4, 0. Okay, so what does that tell us? Well, that tells us that A is equal to 4, C is equal to 5. Remember, A is always the distance from the center to the vertex, and C is always the distance from the focal point to the center. Okay, so before I do anything else, let's sketch the other vertice and focal point. Again, we go equidistant from the center left this time. So our other vertex is negative 4, 0, and our other focal point is negative 5, 0. And then the last thing we need is B in order to complete everything. Now remember, with a hyperbola, A squared plus B squared is equal to C squared. So 4 squared plus B squared is equal to 5 squared. So B is equal to 3. Okay, I can write the equation of this hyperbola now. This hyperbola is going to open up left and right. Let's talk about that first, maybe before I write the equation. Okay, B is 3. The distance from the center to the ends of what we would call the conjugate axis. These are not points that fall anywhere on the graph of a hyperbola, but I'll sketch them in anyways, because that is going to give us the conjugate axis. Okay, so this is the conjugate axis. It kind of just sits there, like in the middle of nowhere. And doesn't really do much as far as the graph is concerned. Sometimes it can give us information about how to write the equation. But let's talk about how I know this opens left and right. So the focal point will always be contained inside of the curves. So what I mean by that is, in order for the hyperbola to go through the vertices and encompass the focal points, it has to open left and right. Another way we could look at that is the vertices are left and right of the center, so the hyperbola will open left and right. Whichever way you can keep track of that, that's fine, but that informs us what our equation is going to look like. So because this opens left and right, it looks like an X So the x term is then what is going to be positive, and a always goes under the positive term, and then the y value in this case is going to be negative, and b always goes under the negative term. Okay. I am just going to sketch this curve. Now, what else do I know? I know that a is 4. So the slopes, if we were calculating the equations of the asymptotes, is 3/4. You guys don't need to show the work on that for your homework. But essentially, if I sketch a line with a slope of 3/4, which is like almost 1. I'm just going to do a really rough sketch here, and then the hyperbola will follow those asymptotes. Okay. All right, so the last thing we need is the eccentricity, always c over a, in this case 5/4. Okay, that's all you've got to do for your homework. Let's do a couple more examples. B, we've got the center at 0, 0. We have a focal point at 0, -8. So 0, -8 down here. A vertex at 0, 4. Okay, so if the center is 0, 0, I go down 4 to get to my other vertice. And then I go up 8 to get to that other focal point. Okay, so what does that mean? Well, that means that A is 4 and C is 8. Distance from the center to the vertice is A. Center to focal point is C. A squared is equal to B squared, A squared plus B squared is equal to C squared in this case for hyperbola. So 4 squared plus B squared is equal to 8 squared. B squared is equal to 64 minus 16. So B is equal to 4√3. Okay, so to get to those, what would be the conjugate axis there? We would go from the center, left and right, 4√3. Okay, so that right there is the conjugate axis. Okay, because from the center we go up and down to get to the vertices, I know this time our hyperbola opens up and down, which makes the y term the positive value there, and then a is going to go under y squared. X is then the negative term, and then b goes under x. That is magnification form. The eccentricity is always c over a, and I will simplify that. Eccentricity is 2 here. The last thing we're going to do is we're just going to sketch the curve. So again, if I was calculating the slopes, it's always change in y over change in x. That is going to be 4/4√3. So we're looking at a slope of plus or minus 1/√3. Again, just sketch. Got my asymptotes somewhere in there. Curve is going to follow those asymptotes, going through the vertice, not the focal point. Okay, then last thing is this. The transverse axis connects the two vertices. All right, on the back, we've got two focal points, 7, 0 and -7, 0. We're told that we've got a vertex at -3, 0. Okay, that means the center is 0, 0. The only point between the two focal points is 0, 0. And that means that our other vertex is 3, 0. Okay, so what do we know? Well, I know that A is 3, C is 7. This is our transverse axis. And then A squared plus B squared is equal to C squared. Okay, so b squared is equal to 49 minus 9. So b is the square root of 40, which is going to simplify to 2 root 10. Okay, so to get to the mark the conjugate axis, we're going to go up and down 2 root 10 from the center. So this is going to be 0, 2 root 10, and this will be 0, negative 2 root 10, and that marks the conjugate axis. Okay, let's write the equation. This is a hyperbola that's going to open left and right. That means that the x term is positive. So a goes under x, and then y is negative, and b goes under y. That's our equation in magnification form. The eccentricity is always c over a. Make sure it's bigger than 1. And then we're going to sketch the curve. So I'm going to draw in my asymptotes here. And make sure that the curve goes through the vertices and not the focal points. There you go. Okay. Moving on, example D. Got 2 vertices here, 0, 6 and 0, negative 6. Okay, that means that our center is 0, 0. That's the point right between those 2 vertices. That means that A is 6. And then what are we told here? So very different piece of information. We are told that a line for the asymptote, one of the asymptotes, is negative 1/3. So we have 2 slopes then. We have slopes that are positive and negative 1/3. So let's take a look. I know that our hyperbola is going to face up and down, because the vertices go up and down from the center. So that means that the y value is positive. The y value is positive. So this is the general form of this hyperbola. Okay, so if we're looking at the slopes, remember slope is always change in y over change in x. So in this case, the slopes are going to be a over b. So I know that our slopes are going to have a relationship or ratio that is 1/3. Okay, what are we told though? We're told that A is 6. And I don't know what B is, so I'm going to set up a ratio and I'm going to cross multiply. B is equal to 18 then. In order for the slope to be plus or minus 1/3 with an up and downward facing hyperbola, B must be 18. All right, so given that information then, I know we're going to go 18 units right and left of the center to get to that conjugate axis. Right. Okay, so this is the conjugate axis. I will label that as CA. This is the transverse axis. I will label that as TA. And then we need C in order to graph the 2 focal points. So A squared plus B squared is equal to C squared. So 6 squared plus 18 squared is equal to C squared. C is equal to, with the calculator, 6 root 10. So to get to those 2 focal points, we're going to go up and down from the center, 6 root 10. So I'll plot that up here, 0, 6 root 10, and then the other focal point will be all the way down here at 0, negative 6 root 10. And sketch in the asymptotes. We're just doing really basic sketches here. You guys did the full sketch on your homework a couple weeks ago. And again, the curve follows the asymptotes, goes through the vertex. Okay, I need the equation. So again, we know that it is up and downward facing, which means y is the positive term here. A was 6. And B we found was 18. That's magnification form. The eccentricity is always C over A. So 6 root 10 over 6. Eccentricity is root 10. All right, center 5, negative 2. 5, negative 2 might look something like this. We've got a focal point at 8, -2. I'm going to mark that over here. And a vertex at 7, -2. All right, so what does that give us? Well, that tells us that A is equal to 2. C is equal to 3. The distance from the center to the focal point is 3 units to the right. The distance from the vertex to the center is 2 units. And then I know that I can plot the other vertice and focal point if I go to the left. So if I go left 2, that's our first vertice. That is going to be 3, -2. And then our other focal point is 2, -2. Okay, transverse axis then connects the center with the vertices. That is our transverse axis. And we use Pythagorean theorem to find B. So 4 plus B squared is equal to 9. B is equal to the square root of 5. So we're going to go up and down the square root of 5 in order to get what we would consider the conjugate axis. So that is going to be the point 5, -2 minus root 5, and this is the point 5, -2 plus root 5. That is the conjugate axis, and we're just going to sketch the curve now. So drop some asymptotes. We know they go through the center. And sketch the curve. Curve goes through the vertices, follows the asymptotes. Looks like that. Okay, this is left and right facing, which means that the x term here is the positive value. Now we do have a shift because the center is 5, -2, so we need to represent that as x minus 5 squared over 2 squared. And then y is what's negative here. This is going to be y plus 2 squared over b, which is root 5 squared, equals 1. That is magnification form, the equation of this, and then the eccentricity then is c over a, which is 3 over 2. Okay, F has a center of -1, 6. I'll say that's -1, 6. We've got a focal point at -1, 2. And a vertex at -1, 8. Okay, what can we get from that then? Well, I know that the distance from the center to the vertex is A. In this case, A is 2. And the distance from the center to a focal point is C. In this case, C is 4. Okay. So that means that my other focal point here is -1, 10. And our other vertex is -1, 4. All right, a squared plus b squared is equal to c squared. 2 squared plus b squared is equal to 4 squared. So b is equal to the square root of 12, which is going to simplify to 2 root 3. All right, so that conjugate axis then, we go left and right 2 root 3. Gets us this point, and this point over here is -1 minus 2 root 3, 6. That is the conjugate axis. Transverse axis connects the vertices and the center. And we are going to sketch the curve. So, asymptotes. And go through the vertices, follow the asymptotes. We have a left and right facing, or excuse me, up and downward facing hyperbola, which means that the y value is the positive value here. Okay, so y minus 6 squared over a squared minus x plus 1 squared over 2 root 3 squared. That is magnification form. And then the eccentricity is C over A. Eccentricity is 2. Okay, last two here. The focus is 3, -6. So a focal point of 3, -6. Let's just graph that. I'm going to put that here. And then we're told this. The vertices are at 3, -4. So let's say I've got a vertice here. And 3, 10. Okay, find the center. That's the first thing that we can do. We've got 2 vertices, so the center has to be right in between those. The x value has to be 3, and then you're finding the point between 10 and -4, so that should be 3. And then we know that A is 7 then. The distance from the center to a vertice is 7 units. That also then gives us C. C is the distance from the center to a focal point. In this case, C is going to be 9. Okay, I can also then get the other focal point. The other focal point is going to be 3, 12. And then we can find B. A squared plus B squared is equal to C squared. 7 squared plus B squared is equal to 9 squared. So in this case, B is going to be 4√2. All right, from the center then, we move 4√2 right and 4√2 left to get that conjugate axis. So 4√2 to the right, that is 3 plus 4√2, 3. And then the same thing to the left. 3 minus 4√3, 3. That is our conjugate axis. Our transverse axis then is what connects the 2 vertices. Sketch the asymptotes. And then follow the asymptotes for the curve. So the curve looks like that. And something like that. We've got an up and downward facing hyperbola, which means the y term is the positive value here. So this is going to be y plus 6 squared over 7 squared minus x minus 3 squared over 4√2 squared. And then the eccentricity is always C over A. 9 over 7 in that case. Okay. Oh, sorry, let me fix that. That is not the center. It should be y minus 3. There we go. Okay, last one. Different pieces of information. So the vertices 5, 7, and -7, 7. So 5, 7, might look something like that. And -7, 7. Okay, so find the center. The center is directly between those two things. The center is going to be -1, 7. It's the point right in the middle. Okay, that also gives us the value of A. So A is the distance from the center to each vertice. The A value here is 6. Okay, and then the last piece of information we're given, very similar to example of D, is the equation of an asymptote. So what really matters is the slope here. The slopes of our asymptotes are going to be plus and minus 5 over 3 then. So here's the deal. We know A is 6, and I know that this is a hyperbola that opens left and right, which means that the standard equation left and right looks like this. X is what's positive. That means that A goes under the X term. Now, slopes of our asymptotes are always change in Y over change in X, so B over A this time. All right, so B over A is equal to the slope from the information that we're given, 5 over 3. But I know that A is 6 from the vertices. So cross multiply here, we get 30 is equal to 3b. That means b has to be 10 in this problem. Okay, so b is 10 in this problem. I know that that gets us the conjugate axis. So I go up and down 10 in order to get to those 2 points on the conjugate axis. Up and down 10, that means negative 117. And this is negative 1, negative 3. That is our conjugate axis. Okay, what connects the two vertices? That is our transverse axis. And the last thing we need is C in order to graph the focal points. So a squared plus b squared is equal to c squared. You got 6 squared plus 10 squared is equal to c squared. 136 is equal to c squared. So that looks like c is equal to 2 root 34. All right, so last thing, the focal points. We go from the center left and right to root 34. So that is going to be negative 1 plus 2 root 34, comma 7. And the other last focal point here is going to be negative 1 minus 2 root 34, comma 7. Sorry, that's kind of messy there. Okay, sketch the asymptotes. And then we just sketch the curve. Through the vertices, we follow the asymptotes. Focal points go on the inside. Now we write the equation. So the center is negative 1, 7. The x term is what's positive. This is x plus 1 squared over a squared, which was 6, minus y minus 7 squared over 10 squared. Magnification form looks like that. And then eccentricity, the last thing, is c over a. So we are going to simplify that. That is going to become root 34 over 3. All right, homework, gonna be following this set of notes. Email me if you got questions.